Somewhere in the southern sky, a single point of light waits for a telescope to find it. Astronomers call that light our nearest neighbour, and they are telling the truth. Alpha Centauri really is the closest star system to our Sun, but the word nearest is quietly hiding a monster. Our furthest spacecraft has flown for almost 50 years and crossed barely 1,000% of the distance to it. Light itself, the fastest thing that exists, needs more than 4 years to make the trip. And here is the part that should unsettle you. Even if humans somehow crossed that gap and arrived alive, they could never again share a single present moment with the Earth they left behind. Welcome to the horrifying distance between neighbours. If these journeys through space are the kind of thing you enjoy, it would honestly mean a lot if you tapped the like button and subscribed. It helps videos like this reach a few more curious people like you. Now, get yourself comfortable. Let's begin. Every few years, someone updates the poster on a classroom wall, and somewhere near the bottom, in small friendly letters, a caption promises that Alpha Centauri is our nearest neighbour. It is a comforting phrase. Neighbour suggests a fence, a shared driveway, a face you might wave to across the street. Nearest suggests you could, if you truly wanted to, walk there. The words are chosen to make the cosmos feel domestic, and they succeed beautifully. When astronomers say that Alpha Centauri is the closest star system to our Sun, they are not exaggerating, and they are not lying. Out of the several hundred billion stars wheeling through our galaxy, this one system genuinely sits closer to us than any other. And that, strangely, is exactly where the trouble begins. Because the moment you ask what nearest actually means, how far, in the plain arithmetic of kilometers and years, the friendly caption on the poster starts to curdle into something far stranger and far more unsettling than any label could ever contain. Start with what is actually out there, because most people picture a single star and stop. Alpha Centauri is not one star. It is three, bound together in a slow gravitational relationship that has lasted billions of years. Two of them, Alpha Centauri A and Alpha Centauri B, are a closely matched pair, one almost a twin of our own Sun, the other slightly smaller and cooler, the two of them circling a shared centre of gravity, the way a pair of dancers turn around one point on the floor. The third is a small, dim, sullen red dwarf called Proxima Centauri, drifting far out on the ragged edge of that system, so faint that no human eye has ever seen it without the help of a telescope. Together they form a trio, a little knot of three suns in the dark, and already, before we have travelled a single kilometre, the tidy word nearest has begun to fracture, because these three stars are not all the same distance from Earth, and the gap between them is going to matter far more than you might expect. Right now, the closest of the three to us is Proxima Centauri, sitting at a distance of roughly 4.24 light-years. Its two brighter companions, Alpha Centauri A and B, ride a little farther out, at about 4.34 light-years. That difference, a tenth of a light-year or so, sounds trivial, almost like a rounding error you could wave away. It is not. A tenth of a light-year is still nearly 1 trillion kilometres, a gulf far larger than our entire planetary solar system. So when someone announces that humanity has reached Alpha Centauri, the honest reply is a question. Which star? Arriving at Proxima would not mean arriving at the Sun-like pair. You could cross an almost unimaginable distance, plant a flag at the red dwarf, and still have a further journey ahead of you to reach the other two. A journey longer than anything human hands have ever built a machine to survive. Nearest, it turns out, is not a single destination. It is at least three of them, stacked one behind the other in the dark. There is a small, almost poetic cruelty buried in the name of that closest star. Proxima is simply the Latin word for nearest. When astronomers found this faint red dwarf and realized it sat closer to us than any other star in the entire sky, they gave it a name that means, quite literally, the near one. And yet even this, the nearest of the nearest, the closest single star to our Sun in all the galaxy, lies more than 4 light-years from the chair you are sitting in. We named it for its closeness, and it is still so far away that the fastest thing in the universe needs more than 4 years merely to arrive. If the one we actually named the near one is this remote, You can already begin to feel what the rest of the galaxy is going to be like. And here is the first place where human intuition quietly betrays us. The phrase light year sounds like a measure of time. It has the word year sitting right there inside it. People hear 4 light years and picture 4 years of travel, the way you might picture a 4-hour drive to another city. But a light year is not a unit of time at all. It is a unit of distance, the distance that light, moving at the fastest speed the universe permits anything to move, covers in 1 full year. And light does not stroll. It crosses about 300,000 kilometers every single second. In the time it takes you to blink, a beam of light could wrap itself around the Earth several times over. Now let that speed run, unbroken, for 1 entire year, and it traces out a line nearly 9.5 trillion kilometers long. That line, that single, ludicrous 9.5 trillion kilometer line, is 1 light year, and the nearest star is more than 4 of them away. Numbers that large stop meaning anything at all. Trillion blurs into billion blurs into million, and the brain, quite sensibly, throws up its hands. So let me hand you a smaller ruler, one that astronomers use inside our own solar system. It is called the astronomical unit, and it is simply the distance from the Earth to the Sun, about 150 million kilometers. That distance already dwarfs anything in human experience. You could line up nearly 12,000 Earths side by side across it. Now, 1 light year contains roughly 63,000 of those astronomical units. 63,000 Earth to Sun distances laid end to end just across a single light year. And Proxima Centauri sits more than 4 light years away. Carry out the multiplication and the nearest star lands at something like 268,000 astronomical units from where you are. 268,000 times the distance to our own star, just to reach the front of the line. That is the true size of the word nearest, and so far nothing we have said has made it feel any smaller. And here a fair question arises, one that deserves a straight answer before we go any further. How could anyone possibly know that number? We have never sent anything even a fraction of the way to Proxima Centauri. So how do we dare to say it sits 268,000 astronomical units away, and to say it with confidence? The answer is one of the quiet triumphs of astronomy, and it relies on nothing more exotic than a trick your own 2 eyes play every waking second. Hold up 1 finger at arm's length and look at it, closing first 1 eye and then the other. The finger appears to jump sideways against the far wall. Even though it has not moved at all, it shifts because you are viewing it from 2 slightly different positions, your left eye and your right. The nearer the finger, the bigger the jump. That apparent shift, born purely of looking from 2 places at once, is called parallax, and it is the foundation on which the entire staircase of cosmic distance is built. Now trade your 2 eyes for something enormously farther apart. As the Earth swings around the Sun across a year, it carries our telescopes from one side of its orbit to the other, 2 vantage points separated by nearly 300 million kilometers, the full width of our path around the Sun. Photograph a nearby star in the depths of winter, then photograph it again in the heart of summer, and that star, like the finger, appears to shift by the tiniest sliver against the fixed backdrop of far more distant stars behind it. Measure the size of that shift, apply the plane geometry a surveyor uses to fix a distant landmark, and the star's distance falls straight out of the arithmetic. No spacecraft required, no assumptions about engines or fuel, just the angle a star traces as we look at it from opposite ends of our own orbit. Proxima Centauri, being the closest star of all, produces the largest such shift of any star in the sky, and even so, that shift is heartbreakingly small, less than a single second of arc, an angle so fine it is comparable to watching a coin edge sideways from tens of kilometers away. Astronomers first pulled off this feat on a nearby star back in the 1800s, and modern instruments have since refined it to staggering precision. So when we say the nearest star is 4.24 light-years away, we are not guessing, and we are not extrapolating from a dream. It is a directly measured fact, wrung out of the sky by the simple act of looking from 2 sides of our orbit, a number as solidly established as the distance to the Moon. And that is exactly what makes it so unsettling. This is not a figure we can argue down or engineer away. It has been measured, checked, and confirmed. The gulf is precisely as wide as it looks. There is one more thing worth settling before we ask why any of this should matter, and it concerns what actually fills the gap between here and there. We tend to picture the solar system ending neatly at Neptune, the outermost planet, as though the Sun's territory had a tidy outer wall. It does not. The Sun's true domain reaches far, far beyond the last planet, and grasping how far is the final piece of just how isolated we really are. Beyond Neptune, the Sun's influence continues outward through a vast, sparse frontier. First comes the heliosphere, the enormous bubble blown by the solar wind, the stream of particles the Sun exhales in every direction, whose edge Voyager 1 crossed only after 35 years of flight. But even that is not the border. Far beyond it, astronomers infer the existence of the Oort cloud, a titanic shell of frozen, icy bodies, the dormant seeds of comets, wrapped around the entire solar system like a faint spherical fog. We have never seen it directly. Its existence is deduced from where long-period comets fall in from, so it belongs, honestly, to the realm of well-founded inference rather than direct sight. But if it is there, as nearly all astronomers believe, it is staggeringly large. Its inner reaches may begin a couple of thousand astronomical units out, and its outer edge may extend to something like 100,000 astronomical units from the Sun, well over a light-year away, and by some estimates a fair fraction of the entire distance to Proxima Centauri. Sit with that for a moment, because it cuts in two directions at once. On one hand, it means the truly empty no-man's land between our star and the next is narrower than the raw distance suggests the Sun's own faint outer territory, and perhaps a matching shell around Alpha Centauri may reach toward one another across the dark, leaving a smaller, strictly empty gap in between. On the other hand, it makes the human scale of the crossing worse, not better, because Voyager 1, our fastest and farthest traveller, will take roughly 300 years merely to reach the inner edge of the Oort cloud, and something like 30,000 years to pass all the way through it, and leave the Sun's domain behind at last. 30,000 years just to escape the outskirts of our own star's territory, and only then would the real journey to Proxima even begin. The Sun does not release its grip at Neptune. It holds on, faintly but genuinely, for more than a light-year in every direction, and merely crossing that grip is itself a labour longer than all of recorded history. You might reasonably ask why anyone should care about a distance this hopeless. Why fix our attention on three stars we may never touch? For a long time, the honest answer was simply that they were there, the closest lights in the dark, the first stop on any imagined map of the galaxy, a natural place to point a dream. But in just the last few years, that abstract longing has been handed something concrete to aim at, because we now have real evidence that at least one of those stars may not be travelling alone through space. Around it, and around its dim red companion, there appear to be worlds. The red dwarf Proxima Centauri is the surer case. Astronomers have confirmed that it hosts planets of its own, including one, discovered back in 2016, that orbits within the star's so-called habitable zone, the narrow band of distances where temperatures could, in principle, allow liquid water to sit on a solid surface. A second, smaller world was later confirmed on a tighter orbit closer in. There have even been hints of a third, still argued over, still unconfirmed, the kind of faint signal that lives in the uncomfortable space between a genuine discovery and an honest mistake. But the headline holds firm. The nearest star to our own is not a barren, empty point of light. It has a family. And at least one member of that family sits squarely in the temperature range we tend to circle in red pen whenever we go looking for places where life might find a foothold. The bigger, brighter, sun-like star Alpha Centauri A is a far harder target its own light, and the glare of its close companion tend to drown out anything faint orbiting nearby. But in 2024, using the James Webb Space Telescope and a special mask designed to blot out the star's overwhelming brightness, astronomers caught sight of something, a faint speck of infrared light sitting about twice the Earth to Sun distance from the star. When they looked again in early 2025, the speck had vanished, which sounds like a failure until you realise that a planet on a stretched, elongated orbit can swing behind or in front of its star and briefly disappear from view. So the team did something clever. They simulated millions of possible orbits, and out of all that mathematics, a single plausible object emerged. A gas giant, roughly the mass of Saturn, tracing a long looping path that keeps it somewhere between 1 and 2 times our own Earth-to-Sun distance from the star. Now, precision matters enormously here, so let me be exact about what this is and what it is not. This world is a candidate, not a confirmed planet. It has been glimpsed, modelled, and argued for carefully in serious scientific papers, but it has not yet been pinned down beyond reasonable doubt. It appears to sit inside the star's habitable zone, but because it looks to be a gas giant rather than a rocky world, no one is suggesting it could hold life as we understand it, and its own discoverers have been refreshingly careful to say that the real test still lies ahead. Astronomers will point their instruments back at Alpha Centauri A and wait to see whether the speck reappears exactly where the orbits predict. If it does, we may have confirmed the closest planet ever directly imaged around a sun-like star. If it does not, it may quietly dissolve back into noise and instrument error. That discipline candidate, not certainty, is precisely the honesty this whole story is going to demand of us again and again. But notice what has happened all the same. The nearest star system has stopped being an empty signpost and started becoming a place, a trio of suns, with at least a handful of worlds circling them, one of which we may soon photograph clearly enough to give a proper name. And the more real a destination becomes, the more the distance to it begins to sting. It is one thing to be separated from nothing in particular. It is another thing entirely to be separated by an almost incomprehensible gulf from somewhere you could actually point to and genuinely want to reach. So let us finally look at that gulf head on. Let us stop hiding behind trillions and light years and shrink the whole impossible thing down to something small enough to hold in your hand. Imagine taking our entire planetary solar system, the Sun at the centre, and every planet out to distant Neptune circling around it, and shrinking that whole spinning disk down until it is the size of a small coin, about 2.5 centimetres across, resting on the desk in front of you. At that scale, the Sun is not even a visible dot. It is a barely there grain sitting at the coin's exact centre. Mercury, Venus, Earth, Mars, all of them are microscopic specks crowded invisibly near that grain. The giant planets, Jupiter and Saturn, and the 2 ice giants beyond them, ride around out near the coin's rim. That coin, that one small circle of metal under your fingertip, contains everything most people ever picture when they say the word space. Every planet, every moon, every landing, every robot, every photograph humanity has ever taken from the surface of another world. All of it fits comfortably inside the coin. Now, keeping that scale fixed exactly where it is, where does the nearest star fall? Not on the desk, not in the room, not in the building. At this scale, Proxima Centauri sits about 110 meters away, farther than the length of a football field, out past the walls of whatever room you are in, across the street, somewhere down the block. And between your coin and that distant grain there is nothing. No other coins along the way, no halfway markers, no islands to rest on. Just a vast, black, unbroken stretch of desk and pavement and empty air, with a single speck of a star waiting silently at the far end. And here is the detail that ought to stop you cold. Our farthest spacecraft, the most distant object human beings have ever launched, after nearly 50 years of unbroken flight, has, at this same scale, crawled only about the width of your hand beyond the coin's edge. It has not even left the desk, and the neighbour is 100 meters down the road. That spacecraft has earned the right to make the distance real, because no analogy quite does it the way an actual machine can. It is Voyager 1, launched in 1977, back when the fastest computers on Earth were slower than the phone in your pocket by a factor of millions. For almost 5 decades it has been falling outward past the orbits of the giant planets, past the edge of the Sun's magnetic bubble, out into true interstellar space, the first object of human making ever to cross that particular threshold. And it is not dawdling. Voyager 1 is moving at about 17 kilometers every second. Not 17 kilometers an hour, 17 kilometers a second, roughly 61,000 kilometers an hour, quick enough to cross the entire United States in a handful of minutes. By every human standard we have, Voyager 1 is tearing through the dark faster than almost anything we have ever built. And in November of 2026, Voyager 1 reaches a milestone that sounds, at first, magnificent. It becomes the first human-made object ever to sit one full light day from Earth, meaning it will be as far away as light itself can travel in 24 hours. At that moment, it will be almost 26 billion kilometers from home, more than 5 times farther out than the planet Neptune. A radio signal leaving it, racing toward us at the speed of light, will take it from entire day to arrive. For a machine built with 1970s technology, now running on a trickle of power weaker than a household light bulb, this is an achievement that borders on the absurd. One full light day. Light itself needs a whole day to bridge the gap between us and our farthest child, and now hold that triumph up against the distance we actually care about. Voyager 1, after half a century of flight, has reached one light day. The nearest star is more than 4 light years away. Sit for a moment with the mismatch between those 2 units a day, set against years. To turn a single light day into a single light year, you would have to multiply it by 365. To reach Proxima, you would need more than 4 light years, well over 1,500 light days. Put another way, our fastest, farthest, most heroic spacecraft, the one we rightly celebrate at every milestone, has so far covered a little over 0.06% of the way to the nearest star. Not 6%, 0.06%, somewhere around 1 part in 1,500 of the whole journey, after 50 years. Moving faster than a rifle bullet the entire time, and remember what Voyager 1 actually represents. This is not some abandoned prototype or a timid first attempt. It is the single farthest, longest flying, most successful deep space traveler our species has ever produced, the high watermark of everything human engineering has managed to hurl into the dark in all of history. Nothing we have ever built has gone farther, or faster, for longer, and this champion, this record holder, this best we have ever done, is essentially nowhere on the road to the nearest star. If our single greatest achievement can cover only 1 part in 1,500 of the trip in 50 years of flight, then the distance is not merely large. It is a different category of thing altogether, a gulf that shrugs off our finest efforts as though they had never even happened. And it gets quietly worse, because Voyager 1 is not even aimed at Alpha Centauri. It is simply coasting outward in whatever direction its planetary tour happened to fling it, and it will wander the galaxy for tens of thousands of years without ever going near our nearest neighbour. But suppose it had been launched perfectly sent on a flawless straight line toward Proxima Centauri, holding that 17 km/s pace the entire way. How long would the trip take? Not centuries. Not a few thousand years. Something on the order of 70,000 years, closer to 73 or 75,000, by the usual reckoning. 70,000 years is not a number that belongs to engineering. It is a number that belongs to anthropology. That is roughly the span of time separating us from the era when our ancestors were first spreading out of Africa, painting on cave walls and shaping the earliest tools we would still recognize as human. Sit with what that would actually require. If some band of early humans had somehow launched a Voyager toward Proxima Centauri at the very dawn of our species, before agriculture, before writing, before the wheel, before every empire and language and religion that has ever risen and fallen, that spacecraft would still be out there tonight. Still falling through the dark, still not arrived. Every migration, every city, every invention, everything that has ever happened to human beings would have played out while the probe was in transit, and it would still have thousands of years of flight left ahead of it before it reached the finish line. That is not a journey in any ordinary sense. It is a crossing longer than the whole story of our species, run across a track so long we can barely make out the far end. At this point, a very reasonable objection rises up, and you may already be forming it. Voyager, you might say, is old. It is a 1970s machine, lifted by chemical rockets and slung outward by the gravity of passing planets. Of course it is slow. We have better ideas now, faster engines, bolder designs, concepts sitting on drawing boards that could leave Voyager standing utterly still. Surely, with the right technology, 70,000 years collapses down into something a determined civilization could actually contemplate. And that objection is entirely fair. It is in fact the exact question that every serious thinker about interstellar travel has been forced to stare directly in the face. But the answer is not the reassuring one you are hoping for, and the reason why is where this story begins to turn genuinely strange. Because there is a trap waiting inside the innocent phrase, "go faster." Our intuition insists that speed is the whole answer, that if 17 kilometers a second buys us a 70,000-year crawl, then simply going 10 times faster, or 100 times faster, will hand us a journey a human civilization could live with. And yes, the arithmetic does shrink. But it does not shrink anywhere near as kindly as you expect, and the effort demanded to purchase each new increment of speed does not rise gently, it detonates. The distance to Alpha Centauri is not a wall you can knock flat by pressing harder on the accelerator. It is a distance so enormous that even speeds we can barely dream of achieving would still demand patience measured against the length of human generations, and every attempt to shorten the trip forces us to pay a price that climbs far faster than the time we manage to claw back. So we arrive at our first uncomfortable truth. The nearest star is nearest only in the sense that, out of an ocean of hundreds of billions of stars, it happens to sit at the very front of the line. On the scale of a coin on your desk, it waits 100 meters down the street, with nothing in between. On the scale of our fastest spacecraft, it lies more than 1,000 times beyond where 50 years of unbroken flight has managed to carry us. On the scale of a single human life, it hides behind some 70,000 years of travel. And we have reached all of these dead ends without once stepping outside the realm of speeds humanity has already achieved. The obvious next move, then, is to go faster, far, far faster, and see just how much of this horrifying distance we can burn away. So, let us do exactly that. Let us take the boldest, fastest journeys human minds have ever dared to imagine, and find out how close they can truly bring the nearest star. We ended on a promise, the same promise every dreamer eventually makes when the arithmetic turns cruel: go faster. Voyager 1 is a museum piece with a nuclear heartbeat, lifted by chemical fire and slung outward by the gravity of passing planets. And of course it crawls. Build something better. Press harder on the accelerator. And surely that monstrous 70,000-year crossing folds down into a number a determined civilization could actually stomach. It is the most natural thought in the world, and it is exactly the thought this part exists to take apart. Because when you actually run the numbers on going faster, not with imaginary engines, but with the real speeds humanity has already reached, you discover something that ordinary intuition never sees coming. The distance to the nearest star does not yield gently to speed. It resists it, absorbs it, swallows enormous multiples of velocity, and hands back only the smallest scraps of time. And to feel why, we need a different ruler than the ones we have used so far. Not a coin on a desk, a human life. So let us fix that ruler in place before we start, because everything in this part is going to be measured against it. Take a long, full human life, call it 80 years, birth to death, a good and complete span by any standard our species has ever known. Take a human generation, the gap from a parent to a child, at roughly 25 years, and take the whole of what we grandly call recorded history. Every written word, every empire, every dynasty, every name we still remember, which reaches back something like 5,000 years, no further. Those three numbers are the true scale of a human being, not the light year, not the astronomical unit, a life, a generation, the few thousand years of everything we have ever bothered to write down. Hold those against the journey to Alpha Centauri, and the distance stops being an abstraction and becomes something that presses directly on the shape of a human existence. Start again then, with the speed we already know. Voyager 1 moves at about 17 kilometers every second, and aimed perfectly at Proxima Centauri, it would arrive in the neighborhood of 73,000 years. Now measure that not in raw years but in the ruler we just built. 73,000 years is more than 900 complete human lifetimes, lived one after another, cradle to grave, each person handing the journey to the next like a torch that never once goes out. It is roughly 3,000 human generations, parent to child to grandchild. repeated until the number stops meaning anything, and it is around 14 or 15 times the entire length of recorded history. Every pharaoh and emperor and revolution we have ever chronicled, stacked end to end more than a dozen times over, just across from our star to the nearest one. That is the trip at the best cruising speed humanity has ever achieved. 900 lifetimes for a single crossing. But Voyager, you insist, is old and slow, and we have done far better since. And that is true, we have. So let us not compare the nearest star to a 1970s probe at all. Let us compare it to the single fastest object human beings have ever built. The outright speed champion of our entire species, the Parker Solar Probe. This spacecraft does something Voyager never could. It dives again and again straight toward the sun, using our own star's gravity to whip itself into a frenzy, and at its closest approaches, it has reached a speed of roughly 190 kilometers per second, something on the order of 690,000 kilometers an hour. Nothing made by human hands has ever moved faster. It is more than 10 times quicker than Voyager. If raw velocity is the answer to the distance, this is the best answer we have ever produced. So point it at Proxima Centauri and let it run. What happens to our 73,000-year crawl when we swap in the fastest machine in human history? It drops genuinely, dramatically, all the way down to something like 7,000 years. And there is the trap, sprung in a single sentence. We took the crown jewel of human propulsion, an object more than 10 times faster than our farthest traveller, and the journey to the nearest star still runs to 7,000 years. That is still longer than all of recorded history. If the Parker Solar Probe had launched toward Proxima at the dawn of the first written language, carrying that record-shattering speed the entire way, it would not be halfway there yet. Our absolute best, our fastest possible, our undisputed champion, and it buys a trip that still outlasts civilization itself. And notice the cheat we quietly allowed ourselves, because it makes the picture even worse. The Parker Solar Probe does not actually travel at that speed in any useful sense. It only touches 190 kilometers per second for a few brief hours at the very bottom of its plunge toward the sun, borrowing that velocity from solar gravity, and then it climbs away and slows right back down, like a stone thrown hard that inevitably falls. That blistering number is not a cruising speed at all. It is a momentary flourish, a speed the probe cannot keep and was never meant to keep. To send anything to Proxima at that pace, you would have to somehow bottle that fleeting velocity and hold it, unbroken, across 4¼ light years of empty space, a feat we have no means whatsoever of accomplishing. And even if we could, even granting ourselves that impossible gift for free, the answer still comes back 7,000 years. The universe barely blinks. This is the pattern that ordinary intuition never grasps, so let us drag it fully into the light and make it undeniable. Speed and time do trade against each other, but the exchange rate on a distance this vast is punishing, and the human ruler makes the punishment obvious. Begin from Voyager's 73,000 years and start buying speed. Double it. Build an engine twice as good as anything that has ever flown, and the trip falls to around 36,000 years. You have doubled the greatest speed in human history, and the crossing is still hundreds of lifetimes long. Go 10 times faster than Voyager, which is already faster than our real champion can cruise, and you land near 7,000 years, still longer than everything we have ever written down. Go 100 times faster than Voyager, a speed that exists only on paper, and the journey finally drops to something like 700 years, 7 centuries. Better, but still, the span from the height of the Middle Ages to today, an unbroken flight so long that whole languages would be born and die aboard the ship before it arrived. And here is the line where the whole problem crystallizes. To bring the journey down to a single human life, to make it possible for one person to be born at launch and, as an old woman, watch Proxima Centauri swell in the window before she dies, you need to go roughly 1,000 times faster than Voyager 1. Not twice as fast. Not 10 times. 1,000 times. And 1,000 times 17 kilometers per second is 17,000 kilometers per second, which is not a modest engineering upgrade at all. It is nearly 6% of the speed of light, 5.7%. To be exact, a velocity so far beyond anything humanity has achieved, or has any working means to achieve, that it belongs to a different conversation entirely. That is the wall this part has been walking you toward. The distance to the nearest star does not fold down into a human lifetime, through ordinary improvement, through better rockets or bolder chemistry, or a clever gravity trick. It surrenders to a lifetime only at a fraction of the speed of light, and reaching a fraction of the speed of light is a problem of a completely different and far more violent kind. Sit with the shape of that, because it overturns the entire instinct we started with. We began this part certain that speed was the answer, that the 70,000-year crawl was merely the fault of old, slow machines. But the crawl is not really a machine problem at all. It is a distance problem. Every reasonable, buildable, imaginable improvement in propulsion, every factor of 2, every factor of 10, every factor of 100 is devoured by 4¼ light years of emptiness and gives back a trip, still measured in centuries or millennia. The only speeds that can defeat the human ruler are relativistic speeds, and those are not improvements to what we do now. They are a leap into physics we have never once touched with anything heavier than a single subatomic particle. But suppose, just suppose, that we made peace with the crawl instead of fighting it. Suppose we stopped demanding that any single traveller live to see the destination, and simply accepted that the journey would outlast everyone who began it. This is the honest logic behind the oldest interstellar idea of all, the generation ship. Do not build a faster engine, build a slower promise. Launch not a probe, but a world, a vessel large enough to carry a living community, one that is born, grows old, and dies in transit, generation after generation, so that the great-great-grandchildren of the founders are the ones who finally arrive. It is a concept. Nothing more, no such ship exists, or is close to existing, and every part of it, from the closed ecology to the social order, remains firmly on the drawing board. But as a way of thinking, it exposes the true cost with brutal clarity. Because a generation ship does not shorten the distance, it simply changes who pays for it. Run the human ruler across such a voyage, and the toll is staggering. Even a relatively swift generation ship, moving far faster than anything we can currently build, might still take many centuries to arrive, which means dozens of generations would be conceived, would live entire lives, and would die inside a metal hull, never having stood on the planet they were sailing toward, and never having known the planet their ancestors left. An entire chain of human beings, hundreds of them, would exist purely as the middle of a journey, not the beginning who chose it, not the end who arrive, but the vast anonymous span in between, born into a corridor between two stars with no memory of one world and no hope of reaching the other in their lifetime. The distance does not go away on a generation ship. It is paid in full by people who never asked to pay it. And notice that we have, once again, quietly waved away the hardest part. To speak of a generation ship at all is to assume you could actually build a world that keeps a community of human beings alive, unassisted, for centuries, and that assumption hides a problem every bit as daunting as the propulsion it tries to sidestep. Think about what such a sealed vessel would truly have to do. It would have to be a complete self-contained world in miniature. Every breath of air scrubbed clean and used again. Every drop of water drunk, passed, purified, and drunk once more. Every scrap of food grown, eaten, composted, and grown afresh, around and around, for hundreds of years, without a single delivery from outside, and without one irreplaceable ingredient ever running out. Our most ambitious sealed ecosystem experiments here on Earth, run for a mere handful of people over a mere handful of years, have struggled and faltered and needed rescuing from the outside air. A starship could never be rescued from the outside air, because there would be no outside air, only the same finite atmosphere, cycling through the same lungs and the same leaves for longer than most nations have existed, and a closed loop like that is a fragile thing. On Earth, when a harvest fails or a disease sweeps through the crops, the wider world absorbs the shock. Food comes from elsewhere while the trouble passes. Aboard a sealed ship there is no elsewhere. A blight that ruins the crops, a fault that poisons the water, a slow imbalance that lets one gas build up and another run thin, any of these, in a world with no reserves and no resupply, could cascade from an inconvenience into a catastrophe with no outside margin to cushion it. The whole system must not merely work, but work in perfect balance, self-correcting, for a span longer than the memory of most civilizations, with everyone's life riding on it every single day. The living machinery is only half of it. The other half is the people, and a small, sealed population turns out to be fragile in ways that have nothing to do with engines. A community aboard such a ship could not be too small, or the slow grind of chance would erode it, and it could not be too large, or the cost of hauling all those extra mouths to a fraction of light speed would climb straight back up the impossible energy curve. Somewhere between those limits sits a narrow band, a village of a few hundred, perhaps a few thousand, souls who must, generation after generation, keep alive not just their bodies but every skill their descendants will one day need. How to repair the reactor, how to tend the crops, how to practice the medicine, how to run the world. Lose a single vital craft to one bad generation that failed to teach it, and there is no library run to the next town over, no expert to summon from a home that swallows every message for years. The knowledge either survives intact aboard that one small hull, taught faithfully from parent to child down a chain hundreds of links long, or it is gone. And with it, perhaps, the mission. There is even a cruel circularity buried in the size of such a world. To be truly self-sufficient for centuries, the ship cannot be a slender dart. It must carry the mass of a small biosphere soil in which to grow crops, water enough to close the cycle, air enough to breathe, workshops, spare materials, and the raw stock to manufacture replacements for anything that breaks. All of that is weight, an enormous weight at that. But every additional ton is a ton that must itself be accelerated toward the stars, and we have already seen how viciously the energy cost climbs with mass and speed together. The more self-sufficient you make the ship, the heavier it becomes. The heavier it becomes, the more impossible it is to move quickly. The more slowly it moves, the longer the voyage lasts, and the longer the voyage lasts, the more self-sufficient the ship must be to survive it. Each requirement feeds the next, tightening like a knot that pulls harder the more you struggle against it. A generation ship is not a single hard problem. It is a nest of hard problems, each one making the others worse. And every one of these calculations, every lifetime and generation and century we have stacked up, has been quietly hiding a second problem, one we raised earlier and can no longer avoid. We keep saying, reach Alpha Centauri as though it were a single place, a door you walk through once. It is not. Remember that this is a system of 3 stars, and they are not sitting together at the same spot. The nearest of them, Proxima Centauri, is the one all our journey times have secretly been aimed at, because it is the closest, but Proxima is a considerable distance out from its 2 brighter siblings, the sun-like pair Alpha Centauri A and B. That inner gap is not small. Proxima orbits the pair at a remove of very roughly a fifth of a light year, something like 13,000 astronomical units, 13,000 times the distance from the Earth to our own Sun. Let that inner distance meet the human ruler too, because it delivers the final blow to the fantasy of arrival. Suppose a crew, against all odds, reaches Proxima Centauri. They have crossed the Great Gulf. They stand, in whatever sense a crew can stand, at the nearest star. Have they reached Alpha Centauri? Only 1/3 of it. To cross from Proxima to the sun-like pair, that inner hop of a fifth of a light year would itself take, at Voyager's speed, something on the order of 3,000 or 4,000 years. The leftover journey between 2 members of the same star system, the part we casually round away when we say the nearest neighbour, is on its own longer than all of recorded history. And even the 2 sun-like stars are not a single target. A and B circle each other on a stretched orbit that carries them anywhere from about 11 to 36 times the Earth to Sun distance apart, so that reaching one is not the same as reaching the other. The nearest star system is not a destination. It is a scattered archipelago of 3 suns, and touching one of its islands leaves you with crossings still ahead of you longer than human history itself. So the word nearest, which cracked once already, now shatters completely under the weight of time. It is nearest across a gulf that our fastest real machine would need 7,000 years to cross. It is nearest at a distance that swallows 1,000-fold increase in speed and still asks for a full human life in return. It is nearest as a place whose 3 stars are themselves separated by journeys longer than civilization. Every honest way we have of measuring it by lifetimes, by generations, by the whole span of the written past returns the same verdict. At any speed humanity has actually achieved, or can achieve through ordinary improvement, the nearest star is not a place a human being can go. It is a place a human being can only aim a long, slow chain of descendants toward and hope. And yet the calculation refused, again and again, to leave us anywhere but one exit. Every path we tried, the champion probe, the doubled engine, the 100-fold leap, even the melancholy patience of the generation ship kept pointing at the same narrow door. The only way to bring the nearest star inside the reach of a single human life is to move at a real fraction of the speed of light. Not 17 kilometers per second, not 190, 17,000, or 30,000, or 60,000 kilometers per second velocities, where the numbers finally, mercifully collapse, where 70,000 years becomes 70, where a person could plausibly outrun the distance instead of merely bequeathing it. That is the promised land. That is the speed that would change everything. But nothing in this universe is faster than it is difficult, and the universe does not hand out fractions of light speed for free. To move a spacecraft at 6%, or 12%, or a fifth of the speed of light is not a matter of building a slightly better engine. It is a matter of pouring in quantities of energy that stagger the imagination, of surviving an emptiness that turns lethal the instant you move fast enough through it, of solving a problem so overlooked that most people never even think to ask it the problem of how, having reached such a speed, you could ever possibly stop. So we have found our door, and it opens onto something far stranger than distance. It opens onto the price the universe charges for speed itself. And that price, the energy, the shielding, the aiming, and the terrible arithmetic of braking is where we go next. Every road we walked led to the same narrow door. If a human being is ever to be born beside our star and die within sight of another, the ship carrying them must move at a real fraction of the speed of light, not 17 kilometers per second, but 17,000, 30,000, 60,000, velocities where 70,000 years of crawling finally collapses into something a single life can hold. We found the door, now we have to pay to walk through it, and the universe, it turns out, does not price speed the way our intuition expects. It does not charge a little more for a little more. It charges savagely, exponentially, at every level at once, in energy, in survival, in aim, and in the one demand almost nobody thinks to ask about until it is far too late. This part is the invoice, and by the end of it, the reason interstellar travel remains a dream and not a schedule will feel less like a failure of ambition and more like a wall built into the structure of reality itself. Begin with energy, because energy is the toll gate you cannot sneak past. There is a simple, merciless piece of physics governing how much it costs to make something move, and it is this: the energy of motion does not grow in step with speed. It grows with the square of speed. Hear that slowly, because the whole tragedy is folded inside it. If you want to go twice as fast, you do not need twice the energy, you need 4 times as much. 10 times as fast demands 100 times the energy. 100 times as fast demands 10,000 times the energy. The bill does not rise as you accelerate, it explodes. And this is before relativity even enters the room. As you push a ship toward a genuine fraction of light speed, the equations of relativity make the curve steeper still, so that the closer you creep to the speed of light, the more energy each additional sliver of velocity consumes, climbing toward a demand that would, at light speed itself, become infinite. This is not an engineering shortfall, it is a calculation from known physics, as solid as anything we understand, and it means that speed is the single most expensive thing you can buy in this universe. Put a number to it, gently, because the number is the point. Take a single sizable crude ship, not a fleet, not a city, just one vessel of perhaps 1,000 tons, modest for something meant to carry living people across the dark. Push it to merely 1/10 of the speed of light, well short of the velocities that would save a human lifetime. The energy of motion locked into that ship, at that speed, works out to something comparable to a substantial fraction of everything human civilization generates. In an entire year, every power plant, every reactor, every burning barrel of oil on Earth, poured into one ship. And that is the theoretical flaw, the energy that ends up purely as motion in a perfect world with no losses at all. Real engines are nowhere near perfect. They waste most of what they consume as heat and light and useless exhaust. Fold in those inefficiencies, and the true energy demand balloons far beyond the clean minimum. To go faster than 1/10 of light speed, which is exactly what saving a human life requires, you climb back onto that squaring curve, and the cost multiplies again and again. The energy needed to fling one crewed ship to the nearest star at survivable speed is not a quantity we are short of. It is a quantity that dwarfs the output of our entire species. This is the hard flaw beneath every propulsion concept humanity has ever sketched, and it is worth walking up the ladder of those concepts to see how each one runs headlong into it. Start at the very bottom rung with the most audacious and most brutally simple idea anyone ever drew up in earnest. In the late 1950s, a team of first-rate physicists and engineers, including some of the finest minds of the atomic age, began serious work on a concept called Project Orion. Its logic was breathtaking in its crudeness. If you want to move something colossal, do not build a delicate engine at all. Instead, drop nuclear bombs out the back of your ship, one after another, and detonate them behind a massive shock-absorbing plate. Each explosion slams against the plate and shoves the whole vessel forward. Then another bomb, another shove, and another a rhythmic pounding of atomic blasts, kicking a spacecraft up to tremendous speed. It sounds like madness, and yet on paper it very nearly worked. Orion was studied with real rigour for years. Its designers ran the numbers, tested scale models driven by conventional explosives, and convinced themselves that a ship pushed by nuclear pulses could carry enormous payloads across the solar system, and that stretched out interstellar versions might, in principle, reach a few % of the speed of light over a voyage of centuries. To grasp how far the idea was actually pushed, consider that its designers did not shy away from the largest versions imaginable. Some sketches at the far end imagined vessels the size of small towns, driven by many thousands of nuclear charges released in sequence, coasting for centuries toward a neighbouring star. The pusher plate, the great slab that would absorb each blast, was not hand-waving either. The team worked hard on how such a plate could survive being struck, over and over, by the fury of a nuclear detonation without vaporizing or shaking the ship to pieces. These were sober calculations by people who understood nuclear weapons better than almost anyone alive. But Orion collided with walls of every kind. The most immediate was legal and moral. Detonating a long string of nuclear weapons in space runs headlong into the treaties that ban exactly that, signed in part to keep the heavens free of atomic fire, and no one relished a launch that would scatter radioactive fallout across the sky on the way up. And even setting all of that aside, an interstellar Orion faced the same tyranny every concept faces. To reach the nearest star in anything short of millennia, it would need a quantity of nuclear devices, so vast, thousands upon thousands of bombs, that the whole scheme buckled under its own scale. So let me be exact, as this story always must be. Project Orion was genuinely studied and genuinely serious, but it was never built, never flown, and, at interstellar scale, never anything more than a bold paper design. It is the first rung on the ladder, and it already brushes the ceiling of what raw brute force can buy. Climb one rung higher to the most credible of the serious proposals: nuclear fusion, the same reaction that lights the sun. In the 1970s, a group of British engineers ran a careful study called Project Daedalus, a design, never built, for an uncrewed probe that would ride controlled fusion explosions up to roughly 12% of the speed of light and coast to a nearby star. A later effort, Project Icarus, revisited and refined the same fusion dream. These were not fantasies scribbled on napkins. They were disciplined engineering studies by serious people, and even they, at 12% of light speed, described a decades-long, one-way, uncrewed flyby that would tear past its target in a matter of hours after cruising for half a century. No human aboard, no stopping. And the fuel requirements strained credibility vast quantities of a rare form of helium that we would essentially have to mine from the atmospheres of the giant planets, because Earth does not hold nearly enough, That is the optimistic end of the ladder. That is the concept that works best on paper. And I must be precise. As this whole story demands, fusion propulsion of this kind has never been built, never been flown, and never been demonstrated. It is a proposed technology, not a proven one. Climb higher, and you reach the boldest real proposal of our own era, and the one that came closest to a plan: Breakthrough Starshot. Its logic was to abandon the heavy ship entirely. Do not carry fuel at all, leave the engine on the ground. Build a colossal array of ground-based lasers with a combined power of around 100 gigawatts, and aim it at a swarm of tiny, gram-scale probes, each trailing a delicate, reflective sail no heavier than a sheet of paper. For a few blazing minutes, the lasers would pour their light onto those sails, and the sheer pressure of that light would drive the little craft up to about 20% of the speed of light fast enough, in principle, to reach the nearest star in roughly 20 years rather than 70,000. It was audacious, and it was taken seriously by serious scientists. And it is, as of the middle of this decade, effectively shelved a program that quietly ran aground on its own staggering difficulties and funding, even as the underlying idea lives on in newer research. The concept endures, the schedule evaporated, and note what even the full dream promised: not a crude vessel, but a fleet of chips lighter than a coin, precisely because the energy wall makes anything heavier impossibly expensive to accelerate. To move people, you would need to scale that 100 gigawatt laser up by factors that leave the realm of engineering for the realm of pure speculation. At the very top of the ladder sits the most concentrated fuel physics permits at all: antimatter. When matter meets antimatter, both are annihilated completely, their entire mass converted into energy with a totality no other reaction approaches. Pound for pound, the most potent fuel the universe allows. On paper, a handful of it could drive a ship to relativistic speed. In reality, humanity has produced only the faintest whisper of antimatter, a few billionths of a gram in total, assembled atom by agonizing atom in enormous particle accelerators at a cost that makes it, gram for gram, almost incomprehensibly the most expensive substance ever made. We cannot manufacture it in useful amounts. We cannot store it, because it destroys any ordinary container the instant it touches one. An antimatter starship is not a blueprint. It is a hope wearing the costume of a blueprint, and honesty requires me to label it exactly that: highly speculative, resting on capabilities we do not possess and have no near path toward. And notice what we have not invoked anywhere on this ladder. There is no warp drive here, no wormhole, no faster-than-light shortcut folding the distance out of existence. Those belong to fiction, not to physics, and physics is the only thing this ship has to sail on. So the energy wall alone would be enough to stop us. But suppose we granted ourselves the energy for free. Imagine some benevolent miracle handed us the power to push a ship to a fifth of the speed of light at no cost. We would immediately collide with the second item on the invoice, and it is one almost nobody sees coming. At relativistic speed, empty space stops being empty. The gulf between the stars is not a perfect vacuum. It is thinly haunted by scattered atoms of hydrogen and by rare drifting grains of dust, so sparse that on the scale of a laboratory, you would call it the finest vacuum imaginable. At walking pace, at flying pace, even at Voyager's pace, this thin haze is utterly harmless. You would never notice it. But energy, remember, grows with the square of speed, and that law does not only govern your ship, it governs everything your ship runs into. Race through that haze at a fifth of the speed of light, and the arithmetic turns lethal. Every single hydrogen atom you strike is no longer a harmless speck. It slams into the hull carrying the energy of the collision, and at these velocities a steady rain of individual atoms becomes a continuous blast of radiation and erosion, sandblasting the leading face of the craft microscopically but relentlessly across 4 light-years of travel, and the atoms are the gentle part. Every so often, rarely, but inevitably over such a distance, the ship meets not an atom but a grain of dust, a mote so small you could lose it in a fingerprint. At a fifth of light speed, that invisible mote arrives carrying the punch of a bullet, and a slightly larger one the punch of a small explosion, striking a hull that has no time whatsoever to react. This is not a hypothetical worry dreamed up to be dramatic. It is precisely why Breakthrough Starshot planned to send not one probe, but a swarm of 1,000, a grim admission that many would simply be shredded en route, and the mission would succeed only if enough survived the crossing. To move fast enough to save a human life is to turn the emptiest, gentlest medium in existence into a shooting gallery, and to spend the entire journey being fired upon by the vacuum itself. And erosion is only the visible half of what that headwind does. At a fifth of the speed of light, the hydrogen atoms the ship plows through do not merely scrape the hull, each one arrives carrying so much energy that the oncoming wind behaves less like dust and more like a sleet of hard radiation, a stream of particles energetic enough to bore straight through ordinary metal and into whatever lies behind it. Blocking the sandblast is one thing. Blocking a penetrating radiation bath that pours in relentlessly for the entire crossing is another problem altogether, and a far heavier one because the shielding that could stop it is itself dead weight that must be dragged up to a fifth of light speed at the same ruinous cost as everything else. Speed does not just scratch the ship, it irradiates it, and there is a matching cruelty pointing the other way. A working starship, its reactor, its engines, the warmth of whatever lives inside it pours out heat constantly, and that heat has to go somewhere. On Earth, we shed warmth into the air and the ground without a thought. Space offers no such mercy. A near-perfect vacuum is a near-perfect insulator. It carries almost nothing away by contact, and a ship can rid itself of heat only slowly, by radiating it away into the dark. Run a powerful engine inside that insulating emptiness, and the vessel faces the strange danger of cooking itself from the inside, even as the interstellar wind blasts it from the front, scorched within and irradiated without, at one and the same time. And the trap tightens on itself, as every trap in this story does. The faster you fly to shorten the crossing, the fiercer the radiation you drive into the hull, and the more heat your straining engine dumps into a void that will not take it. So the very speed you bought to save time demands still more shielding and still more cooling, still more weight, hauled up the same merciless curve. This, too, is not speculation but plain physics. One more line on an invoice that only ever grows. Grant us shielding then, to armour the ship somehow against the sandblast and the sparse bullets of the dark. We arrive at the third item, quieter than the others but no less unforgiving. The problem of aim. We speak of pointing a ship at Alpha Centauri as though the star were a fixed lamp hanging on a wall, waiting patiently for us to arrive. It is nothing of the kind. Alpha Centauri is moving, drifting across the sky, orbiting the galaxy on its own path, and, being three stars locked in a slow gravitational dance, shifting its internal arrangement year by year, as Proxima and the sun-like pair wheel about one another. You are not throwing a dart at a bullseye. You are throwing a dart across a distance so vast that light itself needs 4 years to cross it, at a bullseye that is itself gliding sideways the entire time. And you must aim not at where it is, but at where it will be decades from now, when your ship finally arrives. Over 4 light years, an error in your initial aim of the tiniest fraction of a degree does not put you slightly off target. It puts you wide of the entire system by distances larger than our whole solar system, sailing forever past into the empty dark with no fuel left to correct and no one to call for help. And when your probe does arrive, if it arrives, it must find and photograph a specific tiny world tucked close beside a blinding star, then turn and send that data home across 4+ light years, a signal so faint after crossing that gulf that catching it at all is a feat unto itself. The precision required is not the precision of a marksman. It is the precision of threading a needle you cannot see on a table on the other side of a continent while both you and the needle are moving. And now we reach the item on the invoice that almost no one ever mentions, the one that quietly undoes everything else, the problem of stopping. Look again, very carefully, at what even our boldest concept actually promised. Breakthrough Starshot was never a mission to visit the nearest star. It was a mission to fly past it. Those gram-scale probes, having spent 20 years crossing the dark, would blaze through the entire Alpha Centauri system in a matter of hours, snatching whatever images and measurements they could grab in that brief, screaming pass and then hurtle out the far side, never to slow, never to return, tumbling on into the galaxy forever. They could not stop. And this was not an oversight. It was a confession written into the design, because stopping is, if anything, harder than starting. Here is why braking is the hidden monster. Every joule of energy you poured into accelerating your ship up to a fifth of the speed of light is still there when you arrive, locked into the ship's motion. And to stop, you must get rid of all of it. Slowing down is not coasting to a gentle halt. It is the entire violent, ruinous work of acceleration performed a second time, in reverse. Which means, at minimum, you must double the already civilization-crushing energy budget we started with, pay the whole staggering bill twice over. But it is worse than merely double, because of where the two payments come due. When you launched, you had a whole planet behind you, laser arrays anchored to the ground, fuel depots, the full industrial might of Earth to fling you forward. When you arrive, you have none of that. There is no laser array waiting at Alpha Centauri to catch you. There is no fuel station orbiting Proxima. Whatever you need to shed a fifth of the speed of light, you must have carried with you the entire way, which makes the ship heavier, which makes it cost vastly more to accelerate in the first place, which drives the launch energy back up the squaring curve all over again, each demand feeding the next without end. Every serious idea for solving this, unfurling a vast magnetic sail to drag against the thin, interstellar gas, or skimming the target star's own light and gravity to bleed off speed, remains firmly in the realm of the speculative, untested and unbuilt. And so we arrive at the sentence that captures the entire absurd predicament. We can, just possibly, imagine throwing something at the nearest star. We have no idea how to make it stop there. And even if we solved all of it, the energy, the shielding, the aim, the braking, there remains a final, mundane, grinding demand that the vacuum imposes for free. The ship has to keep working the entire way. A voyage to the nearest star at survivable speed is a journey of decades at the very least, and every hour of it unfolds in an environment that is actively hostile to machines swept by cosmic rays, starved of power and warmth, and utterly, absolutely beyond the reach of repair. There is no rescue crew. There is no replacement part. There is no engineer who can be sent out to fix a failed component 4 light years from the nearest workshop. We have exactly one machine that has run continuously in deep space for a comparable stretch of time, and it is instructive precisely because it is our champion. Voyager 1, flying since 1977, is a marvel, and it is also a slowly dying one. Its instruments switched off one by one to conserve a fading trickle of power. Its systems failing gradually as the decades grind on, kept alive only by engineers reaching across the void with clever fixes because it still hangs close enough to hear us. A relativistic starship would have no such lifeline. It would need to run for decades with near-perfect reliability, entirely alone, with every critical system either flawless or fatally redundant, because the first uncorrectable failure is the end of the mission, and, if there is a crew, the end of them. We struggle to build a car that runs untended for 30 years on a driveway. This is a demand of a different order entirely. And now, before we tally the whole bill, there is one genuinely strange twist to add the single item on this list that does not punish the traveller, but favours them. So far, speed has only cost us energy, shielding, aim, reliability, all of it climbing against us. But at a real fraction of the speed of light, one of the deepest facts in all of physics quietly comes into play, and for once, it works in the crew's favour. Time itself does not flow at the same rate for a fast-moving traveller as it does for the world left behind. This is not a metaphor, and it is not speculation. It is measured, confirmed physics, tested countless times in particles that live measurably longer when hurled through accelerators near light speed, and in atomic clocks flown aboard aircraft that land a whisker out of step with the clocks left on the ground. Move fast enough, and your own clock, your own heartbeat, your own aging all run slightly slow compared to everyone standing still. For a starship, this means the crew would age less than the years the journey takes as measured from Earth. And that sounds at first like the escape hatch we have been hunting for all along, a way to cheat the crushing travel times, to let a crew step across the dark while barely aging at all. But honesty, as ever, demands the precise number, and the precise number is deflating. The effect only turns powerful when you get genuinely, ferociously close to the speed of light within a whisker of it. At the sort of speeds our boldest concepts actually reach, a fifth of light speed or so, the mercy it grants is real but modest. The crew would age only about 2% less than Earth does over the crossing. On a 20-year journey, that is a saving of a few months. Worth having, certainly, but nowhere near enough to turn an impossible voyage into a comfortable one. There is a further wrinkle folded inside it, one that quietly foreshadows trouble we will meet later. Because the crew's clock runs slow, a fast traveller would arrive to find that the destination and the home they left had aged very slightly more than they had. The two ends of the journey would not merely be far apart in space. They would fall a touch out of step in time itself, the movers aging a little less than the still. At a fifth of light speed, it is only a whisper of a difference. But it is a real one, and it hints that speed does not only stretch the distance between two worlds, it can, ever so slightly, pull their very clocks apart. To make time dilation truly dramatic, to shrink a decades-long crossing into a handful of years felt aboard the ship, you would have to travel at 90%, 99%, 99.9% of the speed of light. And here the twist folds straight back into the trap we already know, because those velocities sit at the very steepest part of the energy curve, where the cost of each additional sliver of speed rockets toward the impossible. The faster you go, the more time dilation would help you, and the more absurdly, ruinously unaffordable that speed becomes. The universe offers the mercy and prices it out of reach in the very same breath. So even this, the one law of physics that seemed to be on the traveller's side, ends up deepening the same lesson. The distance does not bend for us. Not even time bends far enough to save us unless we can pay a price that only climbs the harder we ask. So lay the whole invoice out on the table and read the total. To bring the nearest star within a human lifetime, you must reach a fraction of the speed of light. To reach a fraction of the speed of light, you must pour in energy that dwarfs the output of all human civilization and pay it a second time to stop. You must armour a ship against a vacuum that turns lethal the very moment you move fast enough through it. You must aim across 4 light-years at a moving 3-star target with a precision that punishes the slightest error with eternal exile in the dark. And you must build a machine that runs flawlessly, unrepaired, alone, for decades, in the most hostile environment that exists. Not one of these is solved. Several may not be solvable at all. This is why the nearest star, for all our dreaming, has no departure date, not because we lack the will, but because the universe has priced the ticket beyond anything a single world can pay. And yet suppose some future humanity, richer and cleverer and more patient than we can easily imagine, somehow paid every line of this impossible bill. Suppose they mustered the energy, survived the sandblast, threaded the needle across 4 light-years, and most miraculous of all, actually stopped, sliding a living ship into orbit around a world circling the nearest star. Suppose they crossed the horrifying distance and won. You might think that would be the end of the story, that arrival, so dearly bought, would finally close the gap and lay the whole nightmare to rest. It would not, because the distance to Alpha Centauri does not disappear the moment you arrive at Alpha Centauri. It changes into something else, something quieter, and in its own way far worse. And the travellers who crossed all those light years would discover, in their first hours at journey's end, that the gulf they thought they had defeated was still stretched out behind them, unbroken, permanent, and about to reshape every message, every decision, and every human life on both of its shores. That is the discovery waiting on the far side. That is where we go last. Let us give them the miracle. After everything, after the energy that dwarfs civilization, the sandblasting vacuum they somehow survived, the needle threaded across 4 light-years, the impossible arithmetic of stopping, let us simply grant that some future humanity paid the whole bill and won. Picture the moment. A ship, launched generations ago from a blue world circling a yellow star, slides at last into a slow orbit around a planet at the nearest star. The engines that fought so long to shed the ship's terrible speed fall silent. Through the windows, a new sun hangs in the black, perhaps the warm, familiar gold of Alpha Centauri A, so like the star their ancestors left that it aches to look at. Below them turns a world no human eye has ever seen up close. They have done it. They have crossed the horrifying distance. Every calculation in every part of this story said it could not reasonably be done, and they did it anyway. Surely, now, the nightmare is over. Surely the distance so dearly bought is finally behind them. It is not, and the travellers learn this in their very first hours. When someone aboard does the most natural thing imaginable, they send word home. We made it. We are here. We are alive. They point their transmitter back the way they came, toward a pale dot lost in the dark, and they let the message fly at the fastest speed the universe allows, the speed of light, the same speed that governs every radio wave and every laser pulse, and every conceivable signal that will ever exist. And in that instant, as the message leaves, the true nature of the distance reveals itself. Because that triumphant word "we are here" will not reach Earth today. It will not reach Earth this year. It will cross the same 4¼ light years the ship crossed, at light speed, and it will arrive at Earth more than 4 years after it was sent. The people who launched this mission will wait over 4 years, staring at empty sky, before they learn it succeeded. And the crew, having sent it, will wait more than 8 years, 4 for the message to arrive, 4 for any reply to return, before they hear a single human voice answer back. This is the discovery waiting on the far side of the miracle, and it is the cruelest turn in the whole story. The distance to Alpha Centauri does not end when you arrive at Alpha Centauri. It simply stops being a wall you cross and becomes a delay you can never close. You can conquer the space, pour in the energy, survive the crossing, stop the ship, but there is a second distance hidden inside the first, made of pure time, and that one is immune to every trick you used on the first. No better engine touches it. No bolder ship shortens it. Faster rockets, larger antennas, cleverer transmitters, none of it matters in the slightest. Because the message is already moving at the only speed there is, the absolute cosmic limit, and even that is not remotely fast enough. 4 light years, remember, is a measure of distance, but it is also, unavoidably, a measure of the minimum time any word must spend in flight. The star's light you might glimpse tonight left it 4 years ago, and every message you ever send there, or receive from there, inherits that same 4-year exile. The gap is not behind the travellers. It is around them, permanently, woven into every attempt they will ever make to speak to the world that made them. Let us be exact about the shape of this delay, because precision is what makes it real rather than merely poetic. A message from a settlement at Proxima Centauri to Earth takes more than 4 years to arrive. Call it 4¼ years. One way. If those on Earth immediately compose a reply the very instant they receive it, that reply takes another 4¼ years to return. So the fastest possible round trip a question asked and an answer received is roughly 8½ years, and that is before a single human being has spent 1 second actually thinking about how to respond. Add the ordinary human time it takes to read, consider, discuss and decide, and a simple exchange, "What should we do?" answered by, "Here is what you should do realistically," consumes 9 years or more from asking to knowing. 9 years. That is the tempo of every conversation these 2 branches of humanity will ever have. Not a delay you wait out impatiently, the way you might wait for a slow reply, a delay longer than a childhood, a delay in which a person could ask a question, grow measurably older, and still be waiting when the answer finally arrives. Now watch what that single fact does as it spreads outward through every part of the settlers' lives, because it does not stay politely confined to the radio room. It reaches into everything. Consider first the simplest and most brutal case, an emergency. Something goes wrong at the settlement, a failure in the machinery that keeps them breathing, an illness no one aboard knows how to treat, a disaster no plan anticipated. On Earth, in any crisis, there is always, somewhere, someone to call. That instinct is so deep in us we forget it is a luxury of proximity. At Alpha Centauri, the settlers can call. Of course they can. They can broadcast their emergency toward Earth at the speed of light, a desperate plea flung across the dark. And that plea will arrive on Earth more than 4 years after the crisis began. Earth's finest experts can gather, work the problem, and transmit back everything they know, and their answer will arrive at Alpha Centauri more than 4 years after that. By the time any help, any advice, any word of comfort from home reaches the settlers, more than 8 years will have passed. Whatever the emergency was, it will have long since resolved itself, one way or the other. The people who needed rescuing will have either saved themselves without Earth, or they will be dead, and Earth will not even learn which for years, and will send its useless, loving advice into a silence that has already decided everything. Sit with the full weight of that, because it strips away the last comfort we secretly carry about exploration. Every previous frontier in human history, however remote, kept one thin thread back to the rest of us. A thread of rescue, resupply, reinforcement, or at the very least the knowledge that help was coming, even if slowly. A ship lost at sea might still be found. A base at the pole might still be reached. An astronaut in orbit is, at most, a few days and a phone call from home. Alpha Centauri severs that thread completely and forever. There is no rescue that can arrive in time, because the very news of the trouble cannot arrive in time. There is no resupply, because a supply ship would itself take decades to cross the Gulf. There is no reinforcement, no evacuation, no last-minute intervention from the world that sent them. The settlers are, in the most total sense the word has ever carried, alone, not lonely, which is a feeling, but alone, which is a fact of physics. Whatever befalls them without help. Earth can only ever be a witness to their emergencies, and a witness arriving 4 years late watching a fire it cannot possibly put out. And it is not only help that cannot arrive, nothing physical can. It is worth separating two things we usually lump together, because the Gulf treats them very differently. Information, a message, an image, a warning, a design can at least cross the distance, even if it takes more than 4 years to do it, because information can ride on light itself, but matter cannot ride on light. Any physical object, a spare part, a medicine, a tool, a single sack of grain, would have to be flung across the same impossible gulf as the original ship, at the same ruinous cost, over the same span of decades. In practical terms, this means that once the settlement is founded, no cargo will ever again travel between the two worlds. Not once, not ever. There will be no trade, no imports, no shipments, no resupply of any physical thing across that distance, for as long as both worlds exist. Pause on how total that is, because nothing in human history prepares us for it. Every society we have ever built has leaned on others for its stuff. No city feeds itself. No nation mines and grows and manufactures every single thing its people touch. Our entire civilization is a vast web of exchange. This land grows the food, that one pumps the fuel, another forges the metal, a fourth builds the machines, and goods flow endlessly along the threads of that web, so that no one place ever has to make everything. A settlement at Alpha Centauri would be cut out of that web completely and permanently. It could receive knowledge from Earth instructions, discoveries, the design for a new machine, all beamed across as patient light, but it could never receive the machine itself. If the settlers wanted the thing, they would have to build it from scratch, out of whatever raw materials their own world happened to provide, using only the tools they had already made from the tools before those. Consider something as ordinary as a broken part in a life support system, the same kind of failure that, on Earth, a technician fixes in an afternoon with a replacement pulled off a shelf. At the settlement there is no shelf and no factory across town, and no supplier a call away. If the settlers did not already carry a spare, or the machine to make a spare, or the machine to make that machine, then the broken part simply cannot be replaced, not slowly, not expensively, not ever, because the nearest place that could supply it is 4¼ light years away, and no supply run can cross that gap in any human timescale. Every settlement in human history could, in the last resort, send home for what it lacked, and wait for the wagons or the ships. This one could send home, and wait, and no ship would ever come. The waiting would simply be the rest of time. This forces a completeness of self-sufficiency no human community has ever come close to achieving. The settlement would have to be its own farm and its own foundry, its own mine and its own laboratory, its own factory for everything from the largest reactor to the smallest screw. Every element its civilization required, it would have to locate and extract locally, because not one atom would ever be shipped in from home. Every craft, every industry, every specialized skill that Earth's billions casually divide among themselves would have to be held. On Earth, if a single factory in a single country stops making some vital component, the rest of the world can, with effort, supply it. At Alpha Centauri, there is no rest of the world. There is only the settlement, and whatever the settlement cannot make, it will simply never have. So the isolation runs deeper even than the absence of rescue. It is the absence of the entire material lifeline every human society has always taken for granted. Earth can send its distant children ideas across the light years, and it can send them love, and it can send them the accumulated knowledge of the whole species, but it can never again send them a single physical thing they can hold. From the moment of arrival, the settlement is not merely governing itself and defending itself. It is manufacturing its entire world, alone, out of local dirt and local ore, with no delivery ever coming and no delivery ever possible. A colony, in every prior age of human expansion, was a place you kept supplied. This would be a colony that, by the pure arithmetic of the distance, could never be supplied at all. And from that raw fact of unreachable isolation, something profound and inevitable begins to grow, something that reshapes not just how the settlers survive, but who they become. Think about what it means to run a settlement when every instruction from headquarters is more than 4 years out of date on arrival. Imagine Earth, in its wisdom, sending a directive: do this, build that, decide the following. By the time those words cross the gulf and reach the settlement, more than 4 years have passed. The situation the directive was written for no longer exists. The people it was addressed to have moved on, adapted, faced 100 developments Earth could not have known about because those developments had not yet happened or had happened, but their news was still crawling across the dark, not yet arrived. Every command from home describes a world that is already gone. Every order answers a question that was asked more than 4 years ago and has long since been overtaken by events. Earth is not merely slow to respond. Earth is structurally incapable of governing anything at Alpha Centauri, because governance requires knowing the present, and the present at Alpha Centauri is something Earth can never, ever possess. It can only know the settlement's past, and always, unavoidably, a past more than 4 years stale. So the settlers cannot wait for Earth, not because they are rebellious, not because they resent the homeworld, but because the physics leaves them no choice. To survive at all, they must decide now, with what they have, on their own authority, because the alternative is to freeze for 9 years awaiting permission that, when it comes, will answer a question no longer being asked. Every meaningful decision about their own lives must be made locally, immediately, by people standing in the actual present of that distant world, and a community that must make all its own decisions, that cannot in practice be governed from outside, that answers its own emergencies and charts its own course, because no other course is physically possible. That community is not a colony in any ordinary sense. It is becoming something else. It is becoming independent, not by declaration, but by the simple operation of the speed of light. The distance does not merely isolate them. It quietly, inexorably transforms them into their own separate authority, their own separate society, their own separate branch of the human project, because a gulf that no message can close in less than 9 years cannot hold a single civilization together across it. It can only preside over the birth of 2. And here we arrive at the deepest and strangest consequence of all, the one that reaches past politics and survival, into the very texture of what it means to be human together. It is not merely that Earth and the settlement cannot govern each other or rescue each other. It is that they can never share a present. Turn that phrase over slowly, because it is the true heart of this entire story. 2 people standing in the same room share a present. They experience the same moment together and can speak and answer and know one another in real time. Even 2 people on opposite sides of the Earth share a present. Near enough, a voice crosses the planet in a fraction of a second, and a conversation flows. But Earth and Alpha Centauri can never do this. When the settlers look at the most recent message from home, they are looking at Earth's past, at events more than 4 years old, at a world that has already moved on to a present. The settlers will not glimpse for years yet. And when Earth looks at the settlement's transmissions, It too sees only the past, a report from more than 4 years ago, describing a moment that, for the settlers, is already ancient history. Each side is, permanently, watching the other through a 4-year window into a vanished moment. Neither can ever reach the others now. The two branches of humanity can exchange information across the gulf, endlessly and richly, but they can never occupy the same instant of time. They are severed not in space alone, but in the present itself. Consider what that does to something as human as a conversation, and the loss becomes almost unbearably intimate. A conversation, as we have always known it, is a living thing, a back and forth, a call and an answer, two minds meeting in real time and building something together in the moment. Between Earth and Alpha Centauri, that is simply gone, replaced by something that only wears the costume of dialogue. You send a thought into the dark and then you wait not minutes, not hours, but years for a reply. And when the reply finally comes, you have changed. You are older. Your circumstances have shifted. The version of you that asked the question may barely resemble the version that receives the answer. A message might arrive from Earth addressed with warmth and urgency to a settler who, in the 4+ years the message spent crossing the void, has grown old, or moved away, or died, so that a living voice from home speaks tenderly to someone who is no longer there to hear it. Letters would routinely outlive the moods that wrote them, the crises that prompted them, sometimes the very people who sent them. Every exchange between the two worlds would be a kind of correspondence with the past, a series of messages in bottles cast into a 4-year sea, each one describing a world that no longer exists by the time it washes ashore. This is not communication as any human being has ever known it. It is two civilizations writing history at each other, forever out of step, forever describing moments already gone. And so, across years and then decades and then centuries of this, the two branches of humanity would inevitably drift not through any quarrel, not through any decision, but through the sheer impossibility of staying synchronized across a 9-year gulf. Think of how quickly a shared human world diverges even over short separations. Languages shift, slang mutates, customs turn, values move, until people separated for a single generation already struggle to fully understand one another. Now, stretch that separation across a gap where the fastest possible exchange of ideas takes the better part of a decade, where no fashion, no discovery, no shift in thought can pass from one world to the other in less than the time it takes a child to grow. The settlement would develop its own words for the new things it encountered, its own stories about its own sky, its own way of being human, shaped by a world with a different sun and a different past. Earth would move on to concerns the settlers could not follow in real time and would only ever learn about years too late to join. The two would remain kin-bound by shared origin, exchanging their patient, delayed messages across the dark, but they would grow into genuinely separate peoples, two human civilizations developing side by side on opposite shores of a gulf that no amount of goodwill could ever bridge. Not one humanity spread across two stars. Two humanities, related and estranged, speaking to each other's ghosts. This, at last, is the full and horrifying meaning of the distance to Alpha Centauri, and it is nothing like the meaning we began with. We started with a comforting word on a classroom poster nearest, and we have watched it transform, stage by stage, into something monstrous. First we saw that nearest hid a gulf so vast our fastest spacecraft had crossed barely a fraction of it. Then we saw that even the greatest speeds humanity has achieved would spend 70,000 years on the crossing, and that only a fraction of light speed could bring it within a single life. Then we saw the ruinous price of that speed, the energy, the shielding, the aim, the impossible arithmetic of stopping a bill so steep. The journey has no departure date and perhaps never will. And now, having imagined paying every impossible cost and winning the crossing anyway, we find the final cruelty waiting at the end. That arrival does not conquer the distance at all. It only converts the distance from a barrier of space into a barrier of time. And that barrier, made of the delay that light itself cannot outrun, is one we have no power whatsoever to break, because here is the thing that ordinary intuition, right to the very end, refuses to accept. We imagine the distance as a thing you cross once, a hard, heroic, one-time act. after which the crossing is done and the two worlds are joined. But the distance to Alpha Centauri is not something you cross once and finish with. It is something that continues, without pause, for as long as there are people on both sides of it. It sits inside every message, adding its 4-year toll. It sits inside every emergency, ensuring that help can only ever arrive too late. It sits inside every decision, forcing each world to act alone in a present the other can never reach. It sits inside every relationship stretched across the gulf, turning every conversation into correspondence with the past. The travellers who reached Alpha Centauri would not have left the distance behind them at Earth. They would have carried it with them, and it would go on shaping every hour of their lives and their descendants' lives, and every hour of the lives of everyone back home who ever thought of them a permanent, silent third presence in the affairs of two worlds, long after the ship that made the crossing had rusted into memory. And so we arrive at the truth. This whole journey has been circling, not a soft platitude that space is big, and not the false comfort that some future engine will someday make the gap trivial, because the gap that matters most is made of time, and no engine touches it. It leaves us with something far stranger and far more sobering. Suppose humanity truly does it. Suppose we become the kind of civilization that can pour the output of 1,000 worlds into a single ship, that can armour it against the shooting gallery of the vacuum, that can thread it across 4 light years and, miracle of miracles, bring it to a stop around another star. Suppose we conquer the horrifying distance in every way it can possibly be conquered. Even then, we would not have conquered the separation. We would have 2 branches of humanity that can send each other messages but can never share a moment, that can exchange information but can never exchange a present, that can love each other across the dark but only ever 4 years too late. We could master the journey to our nearest neighbouring star and still, utterly and permanently, fail to master the distance, because the distance was never only the space between the stars. It was the gulf of time, hidden inside that space, the 4-year silence that turns every now into a memory before it can ever be shared. Cross it, and you do not join 2 worlds. You begin 2 histories, and the last, quiet horror of the nearest star is this. The moment we finally reached it would not be the moment humanity became one, people spread across the heavens. It would be the moment humanity, gently and forever, split in 2.